Good afternoon, everyone. We will get started here in just 1 minute. Thanks for joining us. This is Diane Lechner with Midland Scientific. Give us one more minute for some folks to log on, and then we'll get started. Thank you. All right, so it's 1 minute after the hour, so we'll go ahead and get started. As I mentioned, my name is Diane Lechner with Midland Scientific. I'm our Vice President of Customer Experience. So I'm here today with our partners, Hach, to co-partner and conduct a webinar for you all. Thank you for joining us. So we've got presenter Eric here today that I'll introduce here in just a second. And then we've got some poll questions throughout to be a little more interactive. If you guys have any questions at any time during it, please make sure to speak up. And thank you guys for joining us today. So, introducing here, I've got Eric Lehman. He's the Sales Development Manager at Hach. He coaches and mentors regional sales managers while also serving as the subject matter expert in water quality instrumentation, product applications, as well as analytical solutions. With 22 years at Hach and 26 years in the water industry, very impressive. Eric brings extensive experience across the industrial markets, and that includes power generation, beverage production, dissolved gas analysis, and laboratory analytics. He holds a Bachelor's of Science degree in biology and chemistry and has presented at a lot of leading industry events, including Power Plant Chemistry Advisory Group for Nuclear, the Apex Chemical Symposium, and the Power Generation Conference. So Eric's passionate about helping water professionals solve complex monitoring challenges through innovative technologies and practical application expertise. So Eric, very impressive introduction. Thank you so much for joining us today, and I will hand it over to you.
Of course, yes. Thank you for that introduction. I really appreciate it. So let's get started. So the main topic of our webinar today is going to be, simplifying cooling water monitoring with a Hach SL1000. Before we get into that, I really want to thank Midland Scientific for hosting this and facilitating this. Midland's been a long-standing distribution partner for Hach, providing instrumentation, reagents, and industrial water solutions to our customers. So, Diane, thank you, and thank you, Midland Scientific. So there's three primary areas we're going to focus on today. One, we're just going to make sure we level set and talk about cooling tower fundamentals. The second one is going to be the product that we're talking about, the SL1000 platform. And then lastly, current state versus future state. So I want you to pay attention to two things, really. How the SL1000 can simplify multiple test methods, save time, reduce human error compared to conventional methods. But then secondly, think about your current state of how you monitor your cooling tower water. What does that look like? How many cooling towers do you have, making your rounds, the time it takes to take those measurements? So just want to have you reflect on that, focus on that. So let's go ahead and jump in and get started. So when we talk about cooling water in the industry, most of you probably know that in some form heat is generated. So whether it's a petrochemical plant, ethanol plant, steel mill, pulp and paper mills, power plants, chemical plants, pharmaceutical, they create this byproduct of heat. And a lot of times it's produced maybe by steam generation or some sort of process within the plant itself. So they need to do something with that byproduct. So what they have to do is cool it down. There's really three main means of cooling that water down. I'm sure you're familiar with these. You might have a want-through type system. So you have your steam from the plant coming into the condenser, coming out, back to the power plant, back to the boiler system. way that works is it uses, say, water from a lake, water from a river, brings that cold water in, cools that steam down, not really coming into contact with the condensate, but uses basically transfers that heat to the cooler water and then discharges it back. So that's considered more of a once through type system. We have an open recirculating system or evaporative system, which we'll get into, and then the closed recirculating system or non-evaporative. Systems like this often use glycol-based coolants, so it's completely closed loop. You don't have the evaporation that you might on an open recirculating cooling tower, so that's why it's more of a non-evaporative closed loop system. The cooling system that we're going to focus on today, and this is primarily what we see in industry, is an open recirculating evaporative type cooling tower. So the way this operates is you have the warm water coming in, that water gets sprayed down. You have upward airflow. So you might have there's a material called fill in these cooling towers. So you have upward airflow where that warm water is starting to evaporate out. It's concentrated down at the bottom with the dissolved solids, and then it's continuously pumped into a cycle or into a circular type motion. Now, with this evaporation, they're very effective, but the evaporation creates a lot of challenges when it comes to controlling them and controlling the chemistry of the cooling tower to make sure they work effectively. Something that we need to discuss when we talk about this type of cooling tower is the cycles of concentration. So we saw in the previous slide how the water evaporates out the top. What happens there is, say we start off with, for example, just 5 liters of water. And as that water starts evaporating out, you lose the volume, but everything, all the impurities become more concentrated in the solution itself. So by the time you get to, if you evaporate out 4 liters, you're only left with 1 liter. You've concentrated that down to a 5x solution. So for example, if we're starting off at 20 milligrams per liter of, we'll just say hardness, after that 5th cycle of concentration, concentrated those impurities down to 100 or up to 100 parts per million. So that's what we consider cycles of concentration. So when they're operating a cooling tower, they're limited by the number of cycles they can run on it before they have to perform a blowdown or get rid of that cycled up water or the concentrated water. So there's some limiting factors when it comes to those impurities. Oftentimes we're looking at calcium hardness, alkalinity, chlorides, sulfate, silica, pH, and temperature. So those are some common parameters they look at for the cycle of concentrations. But in a few more slides, we're going to talk about some other parameters they might be monitoring. So when it comes to the challenges of controlling the water chemistries of cooling towers, think of it like this. Think of it as, and maybe you've seen this before, think of it as a cooling water triangle. Where in the bottom left-hand side, here you have your deposition or your deposits, your otherwise known as scaling, where dissolved minerals are going to precipitate out of solution and attach to surfaces on that cooling tower or in a cooling system. So that's called more scaling or deposition. Think of your shower head at home when you get that scale or that white buildup on the shower head itself. Oftentimes that's probably from, say, calcium coming out of solution in the water itself. So a lot of times high hardness levels, high alkalinity levels, maybe more of a basic type pH environment could form a scale or a deposition on the cooling towers. A lot of times chemical treaters are going to feed some sort of anti-scalant to help prevent or mitigate some of that scaling issue. From there up top here, we have corrosion. So corrosion is really caused by many factors. It can be caused by maybe low pH, maybe an acidic environment. So where they're maybe trying to mitigate the scale, maybe they're adding acid to bring the pH down a little bit. Too much pH could actually cause corrosion. Chlorides is another thing that can really cause corrosion on stainless type material, causes pitting, small deep holes in the metal. So they're really trying to mitigate that. Sometimes they have to feed corrosion inhibitors, so maybe a phosphate type corrosion inhibitor to really protect that metal from any type of corrosion. And then lastly, the biofouling. So the biofouling is that organic growth that can build up on the metal itself. So in some cases, you can have these sulfate-reducing bacteria, or SRBs, that can proliferate under the slime layer, basically producing a byproduct of an acid. So that biofilm can actually cause corrosion on the metal itself. So if you're familiar with the biocides or controlling or preventing biofilm, a lot of times they're feeding sodium hypochlorite or a bleach, maybe a bromine type solution to really prevent any sort of that biofilm growth from happening. And really what they're trying to do is prevent loss of that heat transfer. Again, microbiological induced corrosion, where it's that those SRBs are creating the acid to cause corrosion. And then ultimately, what they're trying to alleviate or eliminate is production downtime. So if you have all this heat that you need to get rid of and you can't do it, that could affect your production, whether it's pulp and paper, chemical production, power production, or even ethanol production. So let's stop here and do a poll. Let's post a poll here. Which cooling tower parameter is the highest priority for you for operation? Options are going to be pH, conductivity, alkalinity, hardness, phosphate, or other. Maybe it's silica, chlorine, iron, or copper. We'll give it a few minutes to get the responses. Yeah, so looks like responses are coming in. So not surprising, hardness at 63%. So that really goes back to that the scaling, right? The scaling of or deposition on those cooling towers. So there's different things you have to do to mitigate that. So the hardness, can be the form of the calcium, magnesium, total hardness. We are going to run some tests for total hardness, so stay tuned on that. Thank you for participating in that poll. Some other parameters we might see when it comes to cooling water or cooling tower management. pH is a big one. Conductivity, we talked about TDS, conductivity, alkalinity, hardness. Sometimes we see iron being monitored to see how much iron is being removed or transported from the cooling tower itself. Turbidity is another big one, maybe organics. Turbidity is a good indication of solids coming through that cooling tower, kind of on that recirc line. So there's a number of ways to run these tests. You might have a professional boiler treatment kit, something like this, big blue box with all the reagents, chemicals, titrators in it. A lot of our water treaters use what's called a DR900 colorimeter. So we have the little powder pillows. They have a colorimeter running test independently. Or you might have the MP4 conductivity pH meter. So you pour the sample right into this little well for pH conductivity. So there's a number of different ways to run these tests. What we're going to talk about today is the SL1000 250 portable parameter analyzer platform. That is a mouthful. So when we talk about the SL platform, really there's two models or two versions that you can choose from. On the left-hand side, you have the SL1000 platform. This is typically what we see being used in cooling tower or cooling water applications. So with this instrument, you have 4 slots or 4 ports for the chem keys, which we'll talk about what chem keys are. But you have 4 ports for chem keys, and then you have 2 ports for EChem. So you can plug in 2 electrochemical sensors or probes into the top of this handheld instrument. The SL250, that accommodates 1 ChemKey port and then 2 EChem ports. So 3 total parameters versus the 6 parallel parameters on the SL1000. So let's talk about chem keys. This is really a game changer when it comes to testing water and parameters in water. It's a revolutionary reagent delivery method. So the chemistry itself is contained in these keys or these chemistry keys. So the benefit of this is you don't have to uh, basically open up powder pillows. You don't have to dispense reagent or sample into reagents. It's built right into the chem key. The instrument itself will read the instrument and actually correct for color and turbidity automatically. So if you have a sample that's slightly turbid or has some background color in it, it's going to do that original blank and then take its measurements. It's done automatically. It does a multi-point analysis on each sample. So it's going to take a minimum of 5 tests or 5 readings, one for the blank, one for turbidity correction, but then it's going to throw out any outliers. So maybe you have bubbles in the sample or bubbles were drawn up into the instrument itself. It's going to detect that and throw those out and then give you an average or a calculation of those other 4 readings. It comes equipped with a checks and balance system. So when the instrument or the chem key is placed into the instrument, it's going to scan it, and it's going to detect a number of different errors. So for example, maybe there's too many noisy air measurements. So maybe the turbidity was too high, maybe too many bubbles. Maybe you had a slug of sample or particulate coming through. It's going to give you an error. Maybe the chem key is not seated properly. Maybe it's damaged. It's going to give you an error warning or error message. So could this be annoying? Maybe, but it's also providing you with an error rather than an incorrect result. So I'd much rather have the instrument tell me, hey, something is wrong with this measurement, rather than in traditional methods, getting a measurement or a reading and having it inaccurate or incorrect. It's going to tell you if you have a used chem key. So maybe I've used a chem key to run a test before. It's going to indicate, hey, you need to replace that. Maybe sample temperature isn't within specs, or maybe have an expired chem key that's no longer usable. Now we're still going to get results, but it's going to tell you, hey, this is expired. Ultimately, it's going to reduce that user error and try to eliminate user error and user input that might be incorrect or incorrect readings. So let's talk about the instrument itself. So as I mentioned, it does have an internal barcode reader. So it's going to read the chem key itself. It's going to determine what type of sample or what parameter you need to measure or want to measure. So it's going to pull up the exact wavelength because it has multiple wavelengths that are built in. It's going to pull up the wavelength. It's going to pull up the parameter. It's going to read that sample blank, and then it's going to draw that sample in. Another key feature of this is it has a heater that can heat the sample up to a specific temperature. So now we get more controlled reaction times compared to if you're running, say, a powder pillow or even say like a test and tube type of reagent or method. Talked a little bit about the probes that are compatible with this. We'll talk more about this here in a few slides. The sample detector. So that's going to be these 2 contacts right here. So basically, once we put the sample into our sample cup, it's basically a conductivity sensor, creates a conductance that's going to tell the instrument that it's in contact with the sample, and it can start drawing sample up into the chem keys. It uses pumps to draw that in, IP54 certification, so it can tolerate some moisture. Obviously, you don't want to drop this into a bucket, but it can tolerate some moisture getting wet. And then we can download information. So as it's taking a reading or taking a measurement, it's going to date and timestamp that particular measurement or that reading. And then from there, what you can do is hook up a USB port to it or a USB cable to it, download information onto a CSV file, and then that could be managed in an Excel program or an Excel spreadsheet. So it really allows you to digitally manage that information as opposed to maybe writing it on a bench sheet. So let's talk about how we actually take measurements with this. So first of all, you have the chem key itself. So you open the chem key, you insert the chem key into the instrument, place it in the sample cup, and then you wait for the results. So let's go ahead and do that. So I have my instrument right here in front of me. Just going to power it on. It's kind of hard to see with the background, but it's telling me to insert a chem key or connect a probe. So let's go ahead and do that. So I have my packet of chem keys right here. This one happens to be total hardness low range. So I'm going to take that out of the packet. Here's my chem key. I'm going to place that into the bottom of the instrument. So we have 4 ports. Let's go ahead and put that into the first port. That's my low range total hardness. Maybe I want to do an alkalinity test. So let's do an alkalinity chem key. I'll put that into the second port, right like that. So now we have one in the first port, second port. And you know what? Let's do another hardness test kit or another hardness test. So open up my packet. Here's my chem key. I have another port available, so I'm just going to put the chem key right into that port, right like that. So now it's telling me I'm going to measure total hardness low range, total alkalinity, and another low range hardness. Now it's telling me to place chem keys into the sample. So I have my sample cup right here already filled up. It's going to drop that right into the sample cup, right like this. Now it's telling me to take the instrument out of the sample, and it's already started its testing. So now it's going to count down on all 3 parameters simultaneously. So it just happens that it takes about 7 minutes for the alkalinity test. So we're going to be waiting a total of 7 minutes before we get our results. So you can tell it's a really easy way to test, to run parameters without having to deal with any sort of reagents or chemistries. Everything's built into those chem keys. So let's pause here really quick. Let's see. Do we want to do it here? Yeah, let's do it here. I want you to think about how many grab samples you typically collect during a normal workday. So this could be, obviously, we could be talking about cooling towers, but maybe there's a waste treatment process, maybe an effluent, maybe some potable water you're testing. But how many grab samples do you typically collect in a normal workday? So think about how many cooling towers you might have, how many times those operators make their rounds to pull samples, how many different samples are they pulling. So let's take a look. Let's look at the polls and submit our answers. I think we have 1 to 2, 3 to 5, 6 to 10, more than 10, or maybe it varies per day. All right. Yeah, so it looks like we're moving around a little bit, jumping around. So it looks like majority of the responses, about 6 to 10 samples per day. Looks like some other ones, 33%. It might vary day by day. So maybe just depends on how the cooling tower is operating. Maybe you're running into some challenges or not. So we'll say 6 to 10 per day. So let's talk about that. So let's think about the reaction time and time comparison. So if we'll call this the current state. And just for example, we're looking at nitrification parameters. So total chlorine, monochloramine, free ammonium nitrate. So for each of these parameters, I need to pull a sample, wait 3 minutes for total chlorine. For free ammonium monochloramine, that's going to be a 12-minute reaction time. For the nitrite, that's a 20-minute reaction time. And then pH conductivity, once it's calibrated, that really doesn't take very long, maybe 1 to 2 minutes. But if I'm running all 4 of these parameters, just the reaction time is going to take about 30 minutes. So that's not including handling the reagents. Maybe I'm using the powder pillows for the total chlorine, opening them up, opening the powder pillows up, measuring out my sample volume, putting the powder pillows in there. Maybe I'm a mixer, maybe I'm a swirler, maybe I'm a shaker. So it depends on how you mix the reagent up. So the total reaction time alone is 30 minutes. When we're talking about the SL1000, we're looking at 8 minutes total. And the reason is the limiting factor here is going to be 8 minutes for that color development or the reaction time for the free ammonium monochloramine. You can see the other ones run 3 minutes, 7, and 1 minute. When it runs the parameters or measures these different parameters, it's running them all simultaneously. So when the 1 minute comes up or the 3 minutes comes up for the total chlorine, it's going to give us our concentration. Once the free ammonium monochloramine comes up, it'll give us concentration. And then after 7 minutes with the nitrite, it gives us our reading. So think about that. So if you have, for example, I was working with a customer that has 3 cooling towers, and they have to pull grab samples. So they have their rounds where they have an operator go out with their little carrying kit and their Nalgene bottles, pulling 4 samples a day. So that's 12 samples a day. If you're waiting 30 minutes, the analysis time alone is 360 minutes. Whereas with a solution like a SL1000, it's a total of 96 minutes. So for those same parameters. Now I know each parameters vary a little bit as far as reaction times, but use this as an example of how can we more effectively and efficiently monitor the parameters or the tests on the cooling towers. So I showed you when I ran the test, I had just my one little sample cup. We do manufacture a multi-parameter or multi-sample sample cup. So here we have independent little wells in the sample cup. So maybe I wanted to test for total chlorine and free chlorine in one sample or 2 different samples. I had maybe some other samples that I wanted to run phosphorus or nitrate in. I can do that using this type of sample cup. But by default, it comes with just that one single sample cup. So here's a list of the ChemKey parameter options that we currently offer. We're constantly trying to evolve and develop more and more parameters for this line, so stay tuned. If there's something on here you typically don't monitor, come back and we may have that in the future. But some of the common parameters that we're looking at are going to be the ones in yellow. So when we're looking at cooling towers, total chlorine, free chlorine, again, as you're adding those oxidants, adding the chlorines to prevent the biofouling, maybe you want to do a total measurement, free chlorine measurement. Alkalinity, we really want to make sure our alkalinity is in control so we're not getting the scaling. Phosphate, maybe you're adding a phosphate corrosion inhibitor. So you're looking at orthophosphorus. That's a great test for this here. Dissolved iron, and then of course hardness. At the beginning of the webinar, we did a little survey. Hardness was the #1 parameter to look for in control, which is something we see often. So we do have options for low range and high range hardness for the ChemKey line. When it comes to the ion selective electrodes or the probes that are compatible with this, so this is just the top image of the SL1000. So we do have 2 ports for any combination of these sensors. Usually for cooling water or cooling towers, pH is fairly common. Conductivity for that TDS value or TDS measurement. Sometimes we'll see maybe ORP if they're trying to look at that the biocide control, the chlorine dosing control. Some of that's done more inline, but usually pH conductivity. But just know if there's other points in the process within your treatment process that you need to look at, maybe ammonia, maybe dissolved oxygen in wastewater. You do have other options with the SL1000 and the SL250. Oh, so it's telling me, so we just got our results back here. So the instrument is telling me hardness to low range is 1 milligram per liter, which makes sense. This is coming off my softener at my house. Total alkalinity, about 180 milligrams per liter, makes a lot of sense. And then the other one is telling me that it's also 1 milligram per liter of low range hardness, but that chem key's expired. So even though it's going to give me a result, it's actually expired, saying, hey, it may not be a good result, but it's still going to give me something. So especially if you're doing some sort of compliance monitoring, EPA reporting, it's going to give you some indication that, hey, you need to replace that chem key. So that's how simple it was to run these 3 parameters. Again, I had another port if I want to do a 4th parameter, or up top here with the selective electrodes. So really just put the chem keys in, dipped it in the sample, continued the presentation. So I was able to do a little multitasking. So let's get back to the presentation. So the step 1, so think about your current state of analysis or your current state of the workflow. In most cases, you're going to collect all the materials. So you want to collect maybe your test kits, maybe your buffer solutions, powder pillows, your pipettes. You go around, your operators are going around to make their rounds. So they're collecting the sample at the base of each of these cooling towers. Maybe at that time they're performing the test, or maybe they have to hand it off, take all of those samples back to the lab to have the lab run the tests. They're going to run the analysis on each of those samples. And then step 6, finally, what they're going to do is manually transcribe that data. So maybe they have bench sheets that they're going to capture the data, write it down. That's probably a fairly typical way customers test for cooling tower. Run tests on the parameters on cooling towers. Let's pause and look at this really quick. So think about how we're running those tests. So after we've collected everything, we have to measure the sample volume. Maybe we're using the 10 mil, maybe 25 mil sample cuvettes. We have to run a sample blank on each of those. We're going to mix the reagents, wait that reaction time, complete the reading. So we read it, log the values. Now we have to do that for each of those tests. So it goes back to that previous slide of how long does it take for us to really run each of those tests? We looked at those reaction times. But let's also think about how long it takes to measure everything out. And each one of these steps that we have where we could introduce user error. The improved workflow. So we have the SL1000 kit. So when you purchase the SL1000, it comes in with a blue kit like this, portable kit. You saw the chem key boxes, so you can store the chem keys right there. So you go up, you collect the kit, you walk out, you pull the grab sample, put your chem keys in the instrument, and you can take your measurements all at one time. And from there, what you can do is download the data, again, onto that CSV file to manage the data digitally. So you have the date and time stamps, more of a electronic paper trail than you would with a bench sheet. So it really streamlines the process of measuring not only cooling tower, but any other water parameters you're currently measuring. So let's think about the current state where there's opportunities for error and variation versus a current state. where the SL platform eliminates or at least mitigates some of those issues. So let's start at the very top. We're not going to go through all of these, but let's focus on a few of them. So scratch sample cell with the colorimetric, colorimeter or spectrophotometer. The SL1000 doesn't use sample cells, right? So that's eliminated. We don't have to worry about that. We don't have to worry about wiping down those sample cells. Improper reaction time. So say we have an operator testing total chlorine. Are they going to wait the full 3 minutes? Maybe they get impatient. Let's just wait 2 minutes. We'll be good. Or maybe they forget about it and wait 5 minutes. With the SL1000, that's going to eliminate that problem. It draws a sample in, waits a certain amount of time, gives you that reaction or gives you that measurement, that result at that specific time. Mixing, again, maybe there's different ways to mix. Are you a shaker? Are you a swirler? Is all of the powder dissolved? Again, with SL1000, we're not worrying about that. Or maybe the multiple blanks, right? So maybe there's sample blanks, maybe there's reagent blanks you have to run. Really, that's eliminated when we're looking at the ChemKey or the SL1000 product line. So there's a number of different improvements between the two methods, eliminating human error, user error, operator error, or at least even mitigating it to a certain extent. So I think there's quite a few benefits from one method to the other. Some of the applications, so we talked about cooling towers or cooling water, absolutely. Maybe boiler applications, boiler treatment, drinking water applications. There's, maybe they're chlorinating, maybe they're chloraminating, where they have to measure the free ammonia, total chlorine, free chlorine, monochloramine. You can do that all at once with that SL1000. Water treaters, water doctors, those chemical providers, the Nelcos, the ChemTreats, the Apollos of the world, where they're actually selling the chemical, controlling the chemical feed into those boilers, into those cooling tower systems. They love this tool because it really streamlines their time, right? It makes their time more efficient. It gives them the actual results, within a few minutes, so they can make decisions on how much chemical they need to feed to control that cooling tower or control that boiler. So it's a great tool for those water treaters. Food and beverage. So we see the SL1000 used in food and beverage, maybe for hardness testing, maybe for parasitic acid. So we have a parasitic acid ChemKey. So there's a number of different applications for this. Pool and spas might be another one. One thing we advise against would be maybe a raw wastewater. So if it's an untreated raw municipal wastewater, maybe even an industrial type wastewater where there's a lot of particulate, a lot of solids, 2,000-3,000 parts per million of solids, the SL1000 is maybe not a good fit for it. You could still use the probes. So if you wanted to use dissolved oxygen probes, maybe you wanted to use the ammonia probes, you could still do that. But for the ChemKeys, we would want to focus more on treated wastewater, so tertiary treatment type wastewater, if you plan on using it in wastewater treatment applications. So let's talk about, again, some of the features and the benefits. We'll wrap this up. One instrument for up to 6 different parameters at one time. It's going to perform the tests in less than half the time than manual steps. And in some cases, we saw that even cut it down even further. No chemical handling. So again, we don't have reagents. We don't have to pipette samples, so we're not looking at sample volume. And then there's no chemical waste. So the ChemKeys can be recycled, but ultimately we don't have that chemical waste. No sample prep, no mixing, no swirling, no shaking, automatic parameter recognition. So we put the any ChemKey into the instrument. It's going to automatically recognize what range we're looking at, what wavelength we're looking at, what parameter we're looking for. So all of that is automated and streamlined. Again, sample volume, we talked about that. We really don't care about the sample volume. We just fill up our little sample cup to the sample line. We're not measuring it out. We're not using pipettes. So it makes it more user-friendly and accurate that way. One instrument, up to 6 parameters, plug and play, dip and done. Really anyone, any skill level can run a test like this. So you don't have to be a trained chemist, trained operator. Really any skill level can run these tests. So really streamlines, make it more accurate, less user error for these type of methods. So just to kind of wrap a few things up here, just want to announce 2026, there's the Fuel Ethanol Laboratory Conference. That's going to be held in Sioux Falls, South Dakota, downtown at the Canopy by Hilton. So it's right downtown there, November 10th and 11th. So make sure you sign up for that. Hach's going to have a booth. Obviously, Midland's going to be there. We attended last year, had a lot of great conversations. So make sure you sign up for that as soon as possible. I know that fills up pretty quick. And then lastly, we do have a promotion, SL1000 promotion for the PPA. So save 10% on the SL1000, SL250, all for a limited time. So you can go to midlandsci.com. So go to Midland Scientific's website for details and take advantage of that current promotion. So let me pause in talking there. I wanted to save some time for questions and answers. Are there any questions that you might have? I think we have about 15, 20 minutes. So we have plenty of time. Any questions that came up regarding testing, the instrument, applications, feel free to come off mute, or if you want to put something into chat, feel free to do so.
Thank you, Eric. That was a great presentation. I do have a question here. For facilities that are still using traditional test kits, where do you typically see the biggest source of error in those results?
Yeah, that's a great question. And I did touch on that a little bit. I pulled up that, current state versus a future state. I think the biggest thing is, first of all, with those sample cells, we'll see a lot of times we might have an operator using their shirt or something to get the fingerprints off. They end up scratching it. Not waiting the correct amount of time for that color to develop. So per the method, colorimetric tests, they need to have that color develop. So not waiting that specific amount of time. Maybe they wait too long and it overdevelops or underdevelops. That's going to affect the readings. In some cases, temperature can really affect measurements and accuracy. So if your sample is too cold or too hot, that's going to affect the measurements. We see that in ammonia. We see that in silica measurements where it's very temperature selective, or sensitive. So you really need to make sure you're looking at that. Colorimetrically, you have to do that manually with the SL platform. That's going to do that automatically for you. So that's a great question.
Looks like we got a question in the chat. Is each chem key a one-time use or multiple use?
Yes, each chem key is a one-time use. So once you use it, it'll give you the message. If you try to use it again, or I'm sorry, if you use it once, it's going to give you the results. If you try to use it again, it's going to scan it and say that that chem key has been used once before. So one of the questions that comes up often is, well, how much is it per test? What's cost per test? There is going to be an increase in cost per test, right? We can break it down if you want to go to Midland's website, compare the powder pillow versus ChemKey. There will be an increase per test, but then I think we have to look at, is it worth it? Is it worth the time that we're saving running multiple parameters at one time? Is it worth getting more accurate results by not having to mix the reagents, waiting a certain amount of time? So there is a pros and cons that you need to weigh, but I think ultimately there is a significant advantage to using a Chemkey method versus maybe just a powder pillow method. It's a good question.
Hey, Eric, what about what parameters should you monitor the closest to prevent like scaling or corrosion issues?
Yeah, so for scaling and corrosion, the main parameters, so hardness is going to be the one for mainly scaling. So again, that calcium hardness is really what precipitates out, attaches to the metals. So hardness is going to be a big one. Alkalinity is another one. Again, that's part of that calcium carbonate, that CaCO3. So I would say calcium or hardness, total hardness, alkalinity, pH. So you want to make sure that pH is balanced so you're not getting that scaling or on the opposite end, corrosion. Those are probably the big ones. I would say hardness, alkalinity for scaling issues. pH, throw pH in there too.
Great, thank you.
Yeah. Anyone else?
All right.
All
Well,
right.
if there aren't any other questions, thank you everyone for attending the webinar today. I believe we will have a copy sent out to all that attended. Huge thank you to Eric and all the folks at Hach for your support. And also thank you for the FELC plug. We're very excited about that upcoming here. It'll be here before we know it. Everyone, I'll give you a few minutes back in the rest of your day and have a wonderful week.
All right. Thank you, everyone. Appreciate it.
Bye.
Thanks for your time.